Everybody's here. Amazing. We got people. We got people and we're going. Okay. And we're recording. Did I hit record? I did, right? Yeah, it's recording. What did we do last time? Let's recall last time. Right. We looked at the theta function. Sum over positive integers f of nt. And we took its Mellin transform. And we realized that that was zeta times the Mellin transform of the test function on one hand. On the other hand, this is equal to, this is for any even test function. F is even and nice. This is what, negative f hat 0 over 2, 1 minus s minus f of 0 over 2s plus the integral from 1 to infinity, theta f of t, t to the s, theta f hat of t, t to the 1 minus s. There's plenty more room, but not, there's no way to make this smaller, is there? I don't want to just see.
Oh yeah, we want to see people.
Okay, let's try that. T dt over t. All right, and this was our meromorphic continuation, analytic away from s and 1 minus s, and then when we divide by f tilde. I wanted to show you, right, and so we took this Mellin transform. This is where we got the analytic continuation and functional equation. And then we looked at negative zeta prime over zeta as being the sum of the Vomgold. And we took that sum and we, exactly, inverse peronded, or inverse Mellin transformed it. Zeta prime zeta of s. We took some nice test function phi, took its Mellin transform, x to the s ds, evaluated this in two ways. One evaluation gave us a sum over the primes, and prime powers, of course. Another evaluation gave us phi, all the poles and residues. So we got one from the pole, and we got a sum over all the zeros, phi tilde of the 0, x to the 0.
And the left-hand side is equivalent with the prime number theorem. Right? Well, it's going to give us something equivalent with the.
Exactly. So this was with phi smooth. This is if phi is nice and smooth. Okay, and what we want to apply it to is something that's not smooth. So far, so good. Now, before we get to that, I wanted to show you Riemann's actual memoir. So let me pause for a second. I see people are still writing. The trouble is you can't see as much as of the board.
There's something a bit strange here. Yeah, like somehow the Zoom panels are taking up way too much of your space. I feel like when I'm teaching online, it doesn't take up that much.
Yeah, I don't know how to minimize them. Okay, so far so good. All right.
I would like to ask a question.
Please.
But I don't want to take up too much time. So if you want to defer it, then I would be open to that. So
why don't you ask it and then I'll, yeah, go ahead.
This question is that it's about using this, like this, you want it to depend on X, like where it cuts off. And so
Yes.
One way to do that would be to say, okay, well, it goes up to X and then from X to X plus 2, it just cuts down. But then the way you've got it here is like actually from like X to like 2X, it cuts down. And so, yeah, I just wanted to know, because sometimes when I've tried to make things work with using like phi of n over x as a cutoff, and it's dependent on x, it didn't work out the way I wanted because there's too much extra space that it was cutting off from. And so I just wanted to like hear from your experience, like when does that work and when does it not work? And are there any tricks to keep in mind?
That is exactly what I plan to do today. Exactly.
Oh, okay, cool.
How to unsmooth this and get the actual on the nose prime number theorem out of this. Okay. So I will answer your question in the course of the hour. It's a good question, an important one. You can't always it's not always that easy. So I wanted to show you that you can really see this in Riemann's memoir. So here's Riemann's memoir, 1859. And here's the Euler product. And this is the gamma function, e to the minus nx, x to the s minus 1 dx. He didn't write dx over x. Har wasn't around just then. He does a slightly different expansion of the zeta function, but and a slightly different sort of functional equation. I wanted to show you. So he gets this completed zeta. This is gamma of s over 2, basically. Pi to the minus s over 2. Zeta of s is invariant under s goes to 1 minus s. He looks at, look at this, psi of x, e to the minus n squared pi x from 1 to infinity. This is n times pi times x. That's your theta function. And what he's going to do is take the Mellin transform of the theta function, dx over x with an x to the s over 2 instead of x to the s, because he has an n squared here. And says, so you do a computation, you see that it's this, by the functional equation for the theta function, which is Poisson summation. You integrate from 1 to infinity and from 0 to 1. You flip the integral from 0 to 1. These integrals you evaluate explicitly, and you get this. So it's all literally right there in Riemann's memoir. Here's a nice quarter plus t squared. I think this is the first instance of a quarter plus t squared, well before spectral theory of anything. And then he says, we're going to make a function. So this is the number of zeros. You compute the number of zeros by a contour integral. And then he says, so he knows how to count the zeros. Where is it? Okay, and then he's going to take log zeta. He's going to take the logarithmic derivative of zeta. And well, something like it. It's log zeta over s, and he takes the derivative with respect to s of that, multiplies by x to the s, and takes an inverse transform and has a 1 over log. So you get something very close to what we had, equals contours. The treatment that I gave, and here is the x to the beta over beta coming out of these integrals. The treatment I gave, this one that gives this form, is due to von Mangold. This is actually from von Mangold himself in 1895, 40 years after Riemann's treatment. So that's why this is called the von Mangold function. Okay, I had the chronology backwards last time. So von Mangold is way after. It's because he gives a slightly different treatment, which is the simpler treatment. Riemann's treatment gives him something like pi of x. Where is it? There's pi of x plus pi of root x, pi being counting the number of primes up to x. When he pulls contours in this other version. Why don't I see it?
Is it a big pi or a small pi?
It's right here. Should be a big pi. Anyway, I also wanted to show you where the Riemann hypothesis is. Does anybody know where it is? It's right here. I don't know how your German is. So what he does is he makes this function xi of t. What's xi of t? It is in this expansion, he replaces s by a half plus it. And he calls that xi of t. So we usually call it just xi of s, but he calls it xi of t, makes a change of variables, replaces s by a half plus it. And now he's studying this function, which for real t is real valued. And here he says, my findings are that there are real zeros, and it seems to me that all the roots are real. I will set aside this investigation for now because it's not essential to what I have to say.
He didn't think there were.
So we now know that he actually computed the first couple of zeros by hand, by the Riemann-Siegel process.
Oh, okay, on the line, you mean?
On the line, yeah.
Oh.
I think it's funny that he writes x to the 3/2 in one line, then tt for t squared in another. Yeah. This was, they didn't systematically, when it was the square, it was easier for somehow to write TT than to write T squared. But if it's T to a funny other power.
Whatever the typewriter could.
Exactly. So anyway, so here's the Riemann hypothesis sitting right here. Das alle Wurzeln real sind.
They're all in the.
All of the zeros of this function are real. In other words, when T is that function, because he's made the change variables, S is a half plus IT.
Okay.
So anyway, so that was Riemann's memoir explicit formula. So Riemann goes on to say he already observes, Riemann observes that, what's it called? Well, first of all, that the Chebyshev function, which is this sum, being asymptotic to x. In other words, if you really could take the indicator function of, so this would be if phi is equal to the indicator function of being less than 1. If phi of y tells you when y is less than 1, then here, can you see this? Let's make that slightly better. Then here, the tilde of s would be 1 over s, as we've seen many times. And here you would get x to the 1. So this is equivalent to the prime number theorem. In fact, I would call this the prime number theorem. You shouldn't be counting primes. You should be counting the natural object, which is Vomgold. He observes that this is equivalent to the real part of all of the zeros being less than 1. So here in this sum, as long as, and it's equivalent, by the way, if there is a single zero on the one line, that will contribute a fluctuation of the order of magnitude of the main term.
Right.
So if and only if all the zeros are strictly less than 1, and that is what remains. So this is, of course, for all zeros. And this is what is finally proved by Hadamard, and de la Vallee Poussin, independently a year after Vomgold gives this version. I don't know if there was a renewed interest in the prime number theorem or something, Gauss's conjecture, but anyway.
Wait, when did Hilbert publish his memoir?
His version of geometry, Euclidean geometry, 1901.
Oh no,
So
I mean the of this stuff. The Riemann, sorry.
Riemann, yeah, sorry, Riemann. Riemann is 1859.
Okay, 1859.
1859. It's right here.
40 years later.
Exactly.
Okay.
Exactly. 1859.
Yeah, my bad. Sorry.
No, not at all. So yeah, it's a long time. It's 40 years goes by between when he says, here's how you should be able to prove the prime number theorem, to when it actually happens.
Whoa, that's a lot of time.
It's a hard problem.
Yeah.
So
what was left for Hadamard to do?
Sorry?
What was left for Hadamard to do? What did he do?
He proved, so he and de la Vallee Poussin independently showed that there are no zeros on the one line.
Okay, and we discussed that already, but Riemann didn't prove that.
Riemann knew that the equivalence, but he didn't know how to establish this.
Okay.
He conjectures, of course, that the real parts of the zeros are all 1/2, or at least the non-trivial ones.
We still don't have a strip, right?
And we still don't have a strip, but these guys give a proof. Now their proof uses, a funny trig identity, which is this, 3 plus 4 cosine theta plus cosine of 2 theta is always positive or non-negative. Now, this is a stupid trig identity. It just comes from the fact that 2 times 1 plus cosine squared is this thing, and it's a square. I'm going to give you a more modern proof that works in much greater generality. It also applies to zeta, but there's a more robust, shall we say, method discovered in 1994 by Jeff Hoff. So this is Hoffstein-Lockhart with some simplifying things in the appendix by Goldfeld-Hoffstein-Lieman. So this is what I want to explain quickly. And then we will, so how to prove that there are no zeros on the one line. I'll give a brief sketch, and then I'll show you how to use that to smooth and unsmooth, since that's what you guys asked about, this this expression. So far, so good?
Yeah, wait, so I have another question.
Please.
So it's possible you already talked about this and I sort of glossed over it, but if you scroll up just like a couple inches, and then, yeah, so there's the sum over row. So it's like like there's the main term and then minus sum over row.
Yep.
And then, so you want to basically show that that's little o of x.
Exactly.
And so, of course, you're going to need, well, okay, presumably you're going to need, if any of those roots are up all the way up to 1, it's going to also like mess up the main term. But so if they're all like less, they still could be like going outward toward 1.
They sure could.
And then so somehow you have to balance like how high up it is and how that would be like how quickly that term's oscillating, or is there decay out from the Mellin transform term?
So you're going to see in a second how this is done, and it's exactly what you said. There's some region. I mean, the fact that there are no zeros. So there's sort of the classical proof. Let me show you how the classical one goes. Okay, so there's no zeros on the one line on 1 plus it, right? So here's our picture. We start the integral over here at 2, just to be in the range of absolute convergence. And then here's 1. So we have a pole at 1, and then we know that there are no zeros on the one line. Well, that means that for any epsilon, if I go to 1 minus epsilon, there's some region here that has no zeros in this whole box. Right? Wherever the zeros are, the zeros might be getting closer and closer, but to get closer and closer, they have to go higher and higher. It's a discrete set. In fact, okay, so we know things like the zeta function is when you multiply by s times 1 minus s, you get an entire function, which is of order 1. In other words, it grows like e to the absolute value of s to the 1 plus epsilon. So it grows like e to the absolute value of s times log s, basically.
This is the growth in the terms that are Steiner-Shapard-Archie.
Yeah. Yeah, exactly. That's what it means for, this has nothing to do with zeta. It's just a fact about analytic functions. And then you have this Hadamard factorization theorem, which we're going to hint at in a second. I think in the interest of time, let me not do the full Hadamard because I want to get to this smoothing, unsmoothing. The Hadamard part is completely standard. It's the smoothing and unsmoothing that I want to sort of highlight as being slightly, I don't know if novel is the right word. Used in this context is not. So, so George, just to answer your question, you get one bit of cancellation from being high, and you get another bit of cancellation from being able to pull the contour inside. Does that make sense? And the
yeah,
smaller
it does,
the epsilon, the higher you can go.
Oh yeah, that makes sense. Like this was all, yeah, I guess. But what about in the smooth version? It's the same principle.
Yep, you'll see.
It's just instead of it being geometrical like this, it's just analytic, like it's on paper with a sum.
Yeah, you'll see what we're gonna do. Okay, I'm glad you guys are excited about this. I like it too. Okay, so so that was just an aside for what to do if you know that there are no zeros on the one line. That's a precursor to what we're about to do in a minute. Let me tell you what this Goldfeld-Hoffstein-Lieman idea is. So if you look, so again, we have zeta of s. Zeta of s is a product over the primes, 1 minus 1 over p to the s inverse. So if I look at log of zeta, so let's look at log of zeta of sigma. When I write sigma, I mean that sigma is like the real part of s. So sigma is a real number. So there's no question about log having the property that a product turns into a sum. So I have a sum over the primes. This is negative log of 1 minus 1 over p to the s, which after many times we now sort of knee-jerk expand this into a series. It's a k positive, and this is 1 over k p to the ks. Okay, and s is sigma. S is sigma. Okay, so 1 over k is non-negative. P to the k sigma is non-negative. The primes are non-negative. So this whole thing is definitely non-negative. So log of zeta is non-negative in the region of absolute convergence.
So it means zeta.
Which
is,
means, yeah, on the real, so what we've proved is something completely trivial. For real values of zeta, there are no zeros. But we already knew from a convergent power series, from a convergent product, that in fact, for the entire real part, greater than 1, it was, so this didn't give us anything.
Right.
Okay. Here's the right way to do this trigonometric trick. It's to consider, so the observation, or the trick, I would say, this is just a brilliant little thing, is that if you take 1 plus p to the it plus p to the minus it, and you square this out, let's see what we get. So obviously this is going to be something that's non-negative. It's already real, so it's the same as just squaring it.
Right.
Because we have complex conjugates here. So I have 1 squared. We'll do the diagonal terms. 1 squared, p to the 2it, p to the minus 2it, and then we have cross terms. So we have this cross term plus 2p to the it. We have this cross term plus 2p to the minus it. And we have the other cross term, this times this, which is just 2.
Right.
Okay, so that tells you what you need to look at. That tells you what you need to look at. You need to look at, so the function that we want to create, let f, given a number t, for fixed t, I'm going to let ft of sigma be the following. I want zeta of s cubed, zeta of sigma cubed, because there's a 1 and a 2 here. I want times zeta of sigma plus it squared, zeta of sigma minus it squared, and a zeta of sigma plus 2it, that's that term, and a zeta of sigma minus 2it.
So you're exponentiating it in a sense.
Exactly. So this is again real valued. It's real valued, so I can take logs. Now, when I take logs and I start opening things up, now it's complex value. So you have to be a little bit careful. But the point is, log of ft of sigma is, if I open this up and I use all of these, what all of these terms are, it's just 1 over k, p to the k sigma times things like p to the minus it and p to the plus it and so on. So this is going to be a sum over the primes, a sum over k, at least 1 over k, p to the k sigma times the zeta cubed brings a factor of 3. This gives me 2p to the minus it. This gives me 2p to the it. This gives me p to the 2it. This gives me p to the minus 2it. Actually, I have these backwards, but whatever. The point being, everything here is non-negative.
So it still preserve the realness of all of this, right? The
Exactly.
positiveness. Okay.
Exactly. So now, so that means that this function f of t, which is real, is the exponent of something that's not 0, which means its exponential is at least 1. Did you follow that? We have something whose log is real and non-negative. So the exponent of that is real and bigger than 1. Okay, now suppose zeta of 1 plus it, 1 plus I times some special value t is 0. Suppose there exists a t so that this happens. Okay, if that happens, zeta is an analytic function. Okay, then zeta of sigma plus it is big O of sigma minus 1 as sigma goes to 1 from the right. So analytic functions, when you have a 0, you have to have a 0 of some integer order. You can't go to 0 by some small fraction. You have to go to 0 by full power of zeta minus 1, or s approaching the 0. Okay. And because the zeta function is the conjugate, if you conjugate the inside, you conjugate the function itself. This implies that zeta of 1 minus it would also be 0, right? There's a symmetry across the imaginary axis. If this one's 0, that one's 0 too. And so we look here. What do we know about? We also know that zeta has a pole of order 1. So this grows like 1 over sigma minus 1 as sigma goes to 1 from the right. Zeta of s itself, zeta of sigma itself. So along the real line, we have a pole. It blows up. It's a simple pole, blows up like sigma minus 1. And now we look at this function. The 2's, really wish I could get rid of this. Okay, there we go. The 2's, well, zeta is analytic. So as sigma goes to 1, it goes to whatever this value is. It might be 0, it might not. I don't care. This is bounded. This thing is bounded by sigma minus 1 squared and another copy. So this is sigma minus 1 to the 4th, these two together. And this is bounded by 1 over sigma minus 1 cubed, sigma minus 1 to the minus 3. And 3 is smaller than 4, which means this would go to 0, but it can't.
Why are the last two terms bounded by 1?
All I'm saying is that it's analytic. So this goes to zeta of 1 plus 2it, which is some finite number, whatever it is. Okay, it might be 0, it might be, it's not blowing up. It does, the only place where zeta blows up is at 1. So t is something other than 1. T is something other than 0. We don't know if it's 0 at 0. Does that make sense?
Yep.
Great. There must be some way to both see. Well, okay. Hopefully I can hear you guys. Okay. So so that is the proof, just that the zeros don't, just that there is no 0. So this implies the real part of all the zeros are less than 1, but actually it implies quite a bit more. So using a little bit more elbow grease and Hadamard's factorization of entire functions, you can get more. Let me skip how you do this, because this I think is well explained in lots of places. You'll get that for t, let's say bigger than 1, and for sigma greater than 1 minus some constant over log t, you'll get in this range that in fact zeta prime over zeta of sigma plus it is bounded by, again, some constant times log t. Okay, so using just these kinds of growth ideas, if there was in this range, if there was a 0, then that 0 would still contradict. We have a little bit of room here between the 4 and the 3. We have a little bit of room, and we can push that room into some 0-free region. Okay, so not only is zeta not 0, but zeta prime over zeta is bounded by log t. It's a simple. Maybe I should make this an exercise. It's not that simple. I mean, you have to think about it quite a bit, or look it up somewhere. But
this is how the standard proof goes, right? You construct a 0-free region, and then that gives you what you need.
You don't need technically a 0-free region if you don't want to get a rate. If you don't want to get a rate, then you can just use the fact that there are no zeros on the one line and just get an asymptotic formula. What I'm about to do is get a rate which is the best. Well, there are better rates, but it's a pretty good rate.
I remember seeing a proof where there's some like powers of logs that you can control things by, and that's like.
We'll do better than any power of log.
Oh, okay, so that's gonna be better.
Yeah. Okay, so let me pause there. Any questions so far? Okay, so far so good. So let's use this. How to use this? How to use this? So again, we're going to do exactly what we did before. We want to study 1 over 2 pi I, an integral over some vertical line, negative zeta prime over zeta of s, phi tilde of s, x to the s ds, where phi of y is the indicator function of y being less than 1, and phi tilde is 1 over s. There's not enough decay here to make this work. So the way we're going to do this, so not enough decay, so we smooth and unsmooth. I don't know why smooth becomes a verb and adds an E, but unsmooth can't possibly be a noun, I guess. So it just, I don't know. Somebody will correct my English. Exactly. Okay. The right way to do this is not to choose particular functions, which is how almost everybody in the literature does it. What I consider the right way, which is the completely standard way. That's the way that they do everything else. But when they get here, they still follow the traditional process. It's so ingrained in what they do. So the way I like to do this, we'll do this by convolution, by Mellin convolution. Okay, so we're going to fix some smooth functions psi with compact support in 1/2 to 2. Okay, so I'm thinking of psi of y as being like, here's 1/2, here's 1, here's 2, it's 0, and then it does something, and then it's 0. So it's non-negative. And I want its total integral. Of course, total integral should be measured with respect to the Haar measure on the space where it lives to be 1. Okay, so it's smooth. We can take as many derivatives as we want. It's just something that looks like this. Sorry? Oh. Maybe worth saying why we care about getting explicit rate in prime number theorem. Once you can save arbitrary powers of log, the prime number theorem is much more flexible to be applied in sieve problems, multiplication problems. Exactly. There are a lot of applications where you'll want more than just a rate, although it is also interesting in its own right. Yeah, thanks, Lewis. Okay, so this function is no good. It's not sufficiently spiky for us. Although we will be able to say things like, if we take the Mellin transform of chi, again, we can save as many powers of s as we want. In particular, we can save 1 power of s, which it turns out will be all we need. But we can save any power of s that we like, again, just by doing integration by parts enough times to turn y to the s into y to the s plus 1 over s, y to the s plus 2 over s times s plus 1, and so on. We get as many powers here as we want. Okay.
Wait, and then, okay, so a quick question about that. When you actually do that, like, do you know how the constant increases with a?
It depends on the derivatives of xi, but actually I'll only do this with a equals 1 in the application. So
it's usually like exponential in the number of derivatives, right?
It depends on, yeah. I mean, this xi, usually you make these functions if you really want to. You're not just hand drawing it. You make it out of things like e to the minus 1 over x squared. That's the prototypical function, which is smooth and non-analytic. It's infinitely differentiable, but it can be 0 over here and still be infinitely differentiable as it picks up greater than once again.
Expand it into the series past.
Exactly. At that point, the series nowhere converges to the value of the function because the series everywhere just 0 identically. Okay. Other questions? All right. So this isn't the function we want. We want to take this function and turn it into a little delta spike. So we're going to fix some epsilon positive and set psi epsilon of y to be 1 over y psi of what?
1 over epsilon.
Sorry, 1 over epsilon and c of. Turns out what we want is y to the 1 over epsilon. It's unusual if you're not used to seeing these kinds of things. And as I said, I have not seen this kind of thing in the literature. I'd be very happy to be proven wrong and see where it is, because I can't believe this is the obvious thing to do. I mean, but this here, the group, yeah, if this is the right thing for the group action, y, then what is the total integral from 0 to infinity of this thing? Well, it's just, let's put in the definition, 1 over epsilon, c of y to the 1 over epsilon, dy over y. We make a change of variables, u is equal to y to the 1 over epsilon, du is equal to 1 over epsilon, y to the 1 over epsilon minus 1 dy. And if I divide both sides by u, here I'll divide by y to the 1 over epsilon, I get dy over y with a factor of 1 over epsilon. In other words, dy over y is epsilon times du over u.
Yes, that goes away.
That's gone. It's still an integral from 0 to infinity, chi of u, du over u, which by assumption was 1. What about the support? Okay, so this still has total integral 1. What about the support? The support is when the inside is between 1/2 and 2. So that's y to the 1 over epsilon being between 1/2 and 2. Which if I raise both sides to the epsilon power means y is between 2 to the epsilon and 2 to the minus epsilon.
What were the requirements for pi again?
Just that it's supported between 1/2 and 2.
That it's smooth.
And that it's smooth, and that its total integral is 1.
Okay, but
And
that's
non-negative.
it, right?
That's
Pi
it.
can be okay. And then you're plugging in y to the 1 over epsilon.
Exactly. I'm making a new function, psi epsilon, out of the fixed function. I'm making a function now that's variable, depending on epsilon. At the end, of course, we're going to choose epsilon optimally. But this is something, so 2 to the epsilon is like 1 plus, big O of epsilon. I don't know, 10 epsilon. And 2 to the minus epsilon is like 1 minus 10 epsilon. Or at least it's bounded by.
Here is that you're sort of adding a spikiness to it by adding that epsilon.
Exactly. And I'm spiking it between 2 to the epsilon and 2 to the minus epsilon.
I was just wondering, how is it that it was intuitive to come up with this?
Yes. Yes, it's the way I came up with this is exactly what's the thing that will integrate correctly with the logarithmic change of variable. This is just taking what everyone does in harmonic analysis and doing it in the multiplicative setting instead of the additive setting. There's nothing new here.
So why are we using the multiplicative harm measure right now?
Because we want the Mellin convolution. We want this Mellin, we want this function exactly, but we can't use this function because there's not enough decay. And the right way to get more decay is to convolve the function you have with the function you want.
Okay.
Or rather convolve to get the function you need for the application. Okay, so let's do that right now. So what is Mellin convolution? What should it mean to take, if I have two functions, f and g, that are on, the positive reals, to the c or whatever, what should their convolution mean? What is this evaluated at some y? Well, I'm going to integrate from 0 to infinity, f, g, d, some dummy variable, du over u. Yeah, I want f of u and g of, yeah, where does the y go? Is it y minus u?
Uy, oh, it wouldn't be like uy inverse?
Exactly, it's y over u.
Multiplicative version.
It's the multiplicative, we have to use the multiplicative group law everywhere. Okay, so that's Mellin convolution. And a simple exercise is that let's make this an exercise. It's a very simple, fun exercise that if you take the convolution and then you take the Mellin transform of S, that is nothing but the product of the Mellin transform. Same as what happens with Fourier. This is nothing but Fourier just
So there's like
Different
harmonic,
group, different hard measure, but yeah, the local global group it works.
Yep.
so hard measure, I mean, sorry, the convolution properties transfer as long as you have suitable groups and.
It's a property of a group action. It's a property of integration along against Haar measure of, it means that we've done everything right. That everything's coming out like this. By the way, how does the Mellin transform of, we should have done this with the Mellin transform here. If I stick in, all right, let me leave it as an exercise, another exercise. I basically did it for you, just another exercise is that if you take chi epsilon and you take its Mellin transform, what you'll get is almost the Mellin transform of chi itself. If you imagine if we stuck in a y to the epsilon here, everything else would go exactly the same, but y to the epsilon is, y to the s. If we stuck in a y to the s, if we were taking a Mellin transform, y to the s would turn into u to the epsilon s. So in fact, that's the Mellin transform. So the reason this, what is the total integral? This is the Mellin transform of chi epsilon at 0, when y to the s with s equals 0. So the reason the value at 0 is also equal to 1 is because the value anywhere is equal to, the value of chi epsilon tilde anywhere is equal to chi epsilon of epsilon times s. Because what is the Mellin transform? It's you take chi epsilon of y, multiply by y to the s, and integrate dy over y.
Oh.
So when s is equal to 0, I get y to the 0.
Okay.
So this calculation that we did is actually a special case of the more general exercise. Okay, so now what do I want to do? So do all of the above, replace psi with, let's call it psi epsilon, which is psi convolved with chi epsilon. Mellin convolved. Okay. So let's look at this function. What can we say about this function? So let's look at it as a value, as a function of y. So if I open this up, the side that I want is the indicator function. This is the indicator function of y being less than 1. So if I open up this integral, it's an integral from 0 to infinity, psi of u, chi epsilon of y over u, du over u. But all that psi does is it cuts off at 1.
This is phi function right now, has no restrictions. I mean, well, you're putting what you want in there.
Exactly. The phi function is exactly the one that I want. The Mellin transform of this phi epsilon function, we already know is going to be the Mellin transform of this, which is 1 over s, times the Mellin transform of this, which is chi tilde of epsilon s. This we know is bounded by 1 over epsilon s. And so here, this is why I don't need anything more than one derivative, because I already have quadratic decay before I even do anything. I pay for it. I pay for it with a 1 over epsilon. We'll have to,
Play around with that, yeah.
exactly. But now I want to understand what this function is and what it does. So let's make some observations here. The observation is, okay, so let's put in what chi epsilon is. Let's do exactly the same change of variables yet again. This is an integral from 0 to 1 of 1 over epsilon chi of, what is it? Y over u to the 1 over epsilon du over u. And we'll make the same change of variables as before if we set v to be y over u to the 1 over epsilon. U is the variable. Then this is u to the minus 1 over epsilon. So dv is the y to the 1 over epsilon just stays where it is. And I get a u, so negative 1 over epsilon comes down. And u to the negative 1 minus epsilon minus 1 du comes out. And now I'm going to divide by v. So when I divide by v, I divide by y to the 1 over epsilon, that's that. I multiply by u to the 1 over epsilon, that's that. And I get du over u with the factor of minus epsilon.
And then your change of variables are pretty insane.
Yep. So when u is 0, y is a positive number. When u is 0, I get infinity. And that minus sign lets me put that infinity up here. And when u is 1, when u is 1, I get a y to the 1 over epsilon. Y to the 1 over epsilon. And then chi of v dv over v. Okay. So far, so good?
Yeah, yeah.
So now let's look at this. I want to understand this function. First of all, what do I know about this function? If I integrate all the way down to 0, I get 1 by chi. So this thing is non-negative. It's non-negative. It's also bounded by 1. Because the most I can get is by integrating it all the way down to 0. If y to the 1 minus epsilon is bigger than 2, then I'm integrating from 2 to infinity, which has no support. So then this phi epsilon of y is identically 0.
So what is y currently here?
So y is just any real number. I want to understand what this function psi epsilon actually looks like.
Okay,
Phi epsilon.
real number like greater equal to 0.
Greater than or equal to 0.
Okay.
Yeah. Yeah. So this is a function on the, so y is some number greater than 0.
Oh, okay.
Okay. And I want to understand what happens to the convolution. The original function phi, if I graph phi, what does phi itself look like? At 1, it's the indicator function of being less than, so it's 1 until you get to 1, and then it's 0 after that. Okay, so this is phi,
What do you want?
which is what I want. So what's this phi epsilon? Well, it's always between 0 and 1. It's always between 0 and 1. Let's look at this condition. This says if y is greater than 2 to the epsilon. 2 to the epsilon is like 1, 1 plus whatever, 10 epsilon or something. So if y is bigger than, so let's see, in another color, if I can do this, I'll draw phi epsilon. Phi epsilon starting at 2 to the epsilon is 0. And if you want to take a guess, until 2 to the minus epsilon, it's going to be 1. So why is that? What color were we using this one? Why do we have this red part of the picture? It's right here.
Yeah.
For the same reason. If y to the 1 over epsilon is less than a half, then this ranges over the full range where chi has support.
Right, yeah.
So phi epsilon of y is identically 1, which is y being less than 2 to the minus epsilon. And in between, it's between 0 and 1. I can't say anything about what it does. It just does something smooth.
I want to ask about this. Okay, so in the real convolution, if we have one good enough, like C undifferentiable, then if I convolve anything, this is C undifferentiable.
Yes.
It's not the same convolution. It's a different convolution.
It's a different
But you
convolution.
still have that problem.
Yeah, because if you want to differentiate this with respect to y, that derivative comes inside and hits g. Or by change of variables, it'll hit f, whichever one is the differentiable one.
Okay, that's one condition. Yeah.
For exactly the same reason. Okay.
Okay.
So now we have the function c epsilon. It's basically equal to the function phi, except on this region, which is of length epsilon. So now let's go back to, okay, so far so good? No questions? So back to 1 over 2 pi I, an integral over the vertical line 2, negative zeta prime over zeta of s, times psi epsilon of s tilde, x to the s ds. Now there's no problem. This has quadratic decay in s. This has quadratic decay in s, using only one derivative.
You're
So,
just plugging it in.
I'm
for
just-
your smooth approximation.
yep.
Okay.
So what do I get? I get a sum over n on one hand, a sum over n Vomgold, and then psi epsilon of n over x. So how does this compare to the sum that I want? This minus the sum that I want, lambda n, the actual phi, differs only on a range of x times epsilon. The integers between x times 2 to the minus epsilon and x times 2 to the plus epsilon are the only ones where there's a difference between these two functions. And what is the, so I can say equals this plus big O, the length of the sum is epsilon x, where they differ. And what's the size of the function on which they differ? It's like log. I'll just crudely bound Vomgold by log x. Okay, so we've got exactly the sum we want up to an error of size epsilon x log x.
Now, choose a good epsilon.
We're going to do it. We're going to choose a good epsilon in a second. First, next thing we're going to do is pull this contour. Okay, so here's how we're going to pull this contour. I have to draw a picture. Here's 1, here's 2. This is what we start out integrating over. And we know that this thing, what we know, I'll remind you, instead of scrolling up and down 1,000 times, that zeta prime over zeta of sigma plus it is bounded by log t on sigma greater than 1 minus some constant over log t. So the graph of this function, 1 minus the constant log t, is this. This is the set of all s where you have equality. So you're approaching the vertical line 1 at the rate 1 over log t. But inside this region, I know that not only do I not have zeros, I have a bound on zeta prime over zeta. So far, so good?
In that region.
In this region, I have this bound.
This was from the theorem, right?
From the, exactly, from the Hadamard, Vallee Poussin, Goldfeld-Hoffstein-Lieman version. So what I'm going to do is choose a parameter t. You see, here, things are good because x is to a small power. Here, things are good because, well, we're going to be integrating from, we have quadratic decay here. So we'll be integrating something 1 over t squared. And so where do we balance those? I don't know. We'll choose a parameter t, and we'll break this integral into the integral from minus t to t, and the integral from t and up. Okay, so we're going to pull contours. So pull contours, getting that this whole thing is equal to, now I'm going to get a residue. I have a pole. I pulled through this pole, so I'm going to get a residue. The residue is still psi epsilon tilde of 1 x to the 1 plus an integral over this curve gamma. So far, so good. By the way, what is this? This is psi tilde of 1 times chi tilde of, well, chi tilde epsilon of 1, which is chi tilde of epsilon times 1. Because the transform of chi, Mellin transform of chi, is just epsilon times the original Mellin transform. Phi epsilon is the convolution. Phi epsilon is exactly this function that we created. It's the convolution of phi and psi epsilon. That's this function, psi epsilon.
And is it
And-
like a meromorphic function?
It's in fact an entire function. Well, it has this 1 over s in front. So it's just the product because because convolution under transforms becomes the product. Where did I write that? Yeah, right here. The convolution turns into the product. That's exactly how we saw that this was equal to the Mellin transform that we want times whatever this Mellin transform is.
You want it to be analytic, so you have no issues pulling the contour.
Exactly. And estimating the contour. Okay, so the point is when I take s equals 1, I get a 1 over 1 and chi tilde of epsilon. Now chi is still a nice smooth function. So chi tilde of epsilon is equal to chi tilde of 1 plus big O of epsilon. Psi tilde of 1 is 1. So I get x times, and what is chi tilde of, sorry, not 1, 0. When epsilon goes to 0, 1 times epsilon goes to 0. What's chi tilde of 0? It's total mass. So chi tilde of 0 is this. So that's also 1. So our main term is x times 1 plus big O of epsilon. In other words, our main term is x plus big O of epsilon x. Which is exactly the main term, which is exactly the error term we already had up to this factor of log. We already had this error term. So this error term can get sucked into that error term.
That's looking at the right side of this.
Yep, we're gonna have errors on both sides. We're gonna put everything to one side and then we'll estimate as best we can. So far, so good. Any questions? We're almost there.
All good up to the computations, right? To do our own time.
Sure. Okay, so let's look at this integral over gamma. We've broken this up into two pieces. And in
Oh yeah, those facts that you said that we should know, those they don't require anything fancy, right?
these ones?
No, the ones up top, the bounds on zeta prime over zeta. And I think, yeah, I have seen elementary proofs of this, nothing.
This uses things like Hadamard's factorization.
Right.
So it's not entirely trivial.
But it's nothing like post one semester complex analysis.
Yeah, exactly.
Right.
Exactly.
Yeah, it's not a.
If you guys want, we can do this argument also. I
No,
wanted to
no.
try to get to this smoothing and unsmoothing.
Yeah, no, it's okay. Yeah, you
Okay.
can get that. Yeah, I just want to make sure that is what I remember seeing somewhere else. Yeah, I'm pretty sure.
Great. Okay, so what's left is to analyze this term, this integral. Okay, so let's try to understand it. So the integral over gamma, we've split into an integral from t to infinity, and of course minus infinity to minus t, plus an integral from minus t to t. Okay.
Pulling the part that's up top, it just dies out.
Yes.
The top and bottom.
Why?
Yeah, that's-
Because this thing decays like 1 over s squared.
Oh, that's what's gonna give you the.
Yep.
Those parts.
So when s is large, you're pulling these little segments up larger, farther and farther. This thing is just killing you. Okay. All right. Let's handle the integral. So let's do both. So on the integral from t to infinity, what can we bound this by? So again, what is it that we're integrating? Zeta prime over zeta. Zeta prime over zeta in this entire region is bounded by log t. So this is an integral from t to infinity. I can bound it by log t. What can I bound phi epsilon by? Remember, we have this 1 over s, where is it here? 1 over s squared, but with a cost of 1 over epsilon. So that's the bound that I'm going to put on phi epsilon. So I get a 1 over epsilon t squared, right? The real part isn't changing. The real part's between 1/2 and 2 or something. So that's not going to give me any cancellation, but in the large t, it's the absolute value of s is like the absolute value of t. Then what do I have? I have so that was this term, and then an x to the s. There's really nothing I can do about this x to the s, but s, the real part's going to get closer and closer to 1. So I'm just going to estimate this crudely by x to the 1. X to the s is estimated by x to the real part of s, and the real part of s is at most 1. So I'm gaining nothing out of the x variable, and ds becomes dt. Okay, so in the integral from t up to infinity, this is the bound.
And this, symmetric for the bottom.
And a symmetric thing for the bottom.
Yeah.
So what do we get out of this? I have an x over epsilon, so this is bounded by x over epsilon, and almost 1 over t. See, the point is that this log t over t squared converges.
Sorry.
Log t over t
Yeah,
squared
yeah.
converges at infinity. That's integrable, which means its tail goes to 0. And what's the rate? Well, I can even pull out a t to the 1/2 and it still converges. This t to the minus 3/2 over log t converges to an absolute constant. That t to the 1/2 I can give a lower bound by t to the 1/2. Yep, just to be crude.
But in reality, it's log t over t, right?
In reality, it's like it's probably, yeah, log t on top and t on the bottom. Yeah. But you have to be a little more careful than actually one needs to be, since I won't be careful with any constants. So I can afford to lose powers of t. So this is very crude. This is very crude.
And can you get like a substantially better result if you're
No.
not crude? It doesn't make it.
As you'll see in a minute,
Okay.
it'll make no difference what the power of t is. It'll change the constant involved in the end.
Better
But-
or worse constant.
Yeah, but not the shape of the error term. Okay, so far so good. And now let's integrate from minus t to t. So what can we say about the integral from minus t to t? Okay, so I have an integral from minus t to t. Zeta prime over zeta, again, I'm going to come back again and again to this bound. It's bounded by log t. Log, maybe now I should be a little careful, like 3 plus absolute value of t, since t is going through 0. Right? This is the bound when t is bigger than 1. When t is near 0, okay, fine, do something else. It's just bounded there. What else do I have? I have this zeta, I have this phi tilde of s. Again, I'm going to bound that by 1 over epsilon times s squared. S squared I can bound by 2 plus t squared or something. The 2 is just there to make sure I don't have blow up at 0. 1, I can put a 1 here. Then an x to the rho, x to the sigma. But now in this entire region, I have a better power of x that I can take. This is where I will win. Because in this entire region, the real part is at most 1 minus some constant over log big T. On this entire region, I get x to a power 1 minus some constant over log t dt. Does everybody see that? So on the large t region, we win because this thing converges, but we don't get anything out of the x. On the small t region, we win because we can go inside the one line by some amount.
Analysis for, right?
That's exactly. Okay, so what do we get here? I have an integral from minus t to t. So let's take this part out. I have x to the 1 minus some constant over log t. I have a 1 over epsilon. That's bad. And then I have a completely convergent integral, log t over t squared. That's just a constant. That's it. There's a log of t times 1 over t squared. It's just integrable. Doesn't matter, take t out to minus infinity to infinity. It's just bounded.
Oh, that's what you're saying.
Yeah, the rest is just integrable. Okay? So let's put everything together. Put it all together. Put all together.
A little unclear on what our contour is doing right now. What does our contour look like?
So this is the region from minus t to t, where the contour is where sigma is equal to 1 minus a constant over log t, little t as t changes.
Okay, so
And
we're doing
all-
that from minus t to t. And then what are we doing above t and below t?
Oh, above t and below, well, I'm always
Below
following this contour. I'm
Okay,
always following this contour.
we're just breaking it up into those pieces.
We're just estimating it differently for the different pieces, exactly. You see, when little t is small, when little t is in this range, we win because we're inside the one line by some amount. When little t is large, we win because we have decay. And we have to balance those two against each other.
Okay, and so then implicitly, there's also like a minus L and a plus L that are going to infinity with the horizontal pieces.
There's a minus L and plus L
Like,
going
'cause
to,
we have to go across and connect to the two lines somewhere.
oh, the two line, you mean?
Because isn't it like that shape, and then we have to go cut over to the two line, but we're like sending those top and bottom pieces to infinity.
Yes, exactly. So what's really
Okay.
going on is something like this. Let me go up higher.
Yeah,
And these parts,
those things are
Exactly.
being sent to infinity, and we talked about why they go to zero.
yes,
Okay.
but by this
That's-
1/s².
Okay, and I just wanted to make sure that that happening was different from the t and minus t, like the t and minus t
Yes.
where our horizontal pieces are or something.
Yes, that I already sent to infinity with, implicitly without even saying.
Yeah, okay. I'm all clear then. Thank you.
Great. So we took this contour, we pulled over, we sent these all the way up. So now we have just this contour. And then this contour we broke up into the small t and large t.
In the original naive way to pull it is pull it directly over the one line. Like, so
Yes,
the super like, oh, this is tech, and then this is what we're doing to formally.
yeah. So doing this gives us a better error term. If you just want little o, if you just want an asymptotic formula, then what Riemann was doing was already enough, which is he went up to the one line at some height t.
We like avoid the pole.
Well, you pass this pole.
Right.
Oh,
That's what-
yeah, you don't know where the other poles are, the poles of zeta prime over zeta, which are the zeros of zeta. And then you go inside by some epsilon and then around. So this was the Riemann's version, and we're doing something very slightly more sophisticated to get an error rate.
And this curve that you, 1/log curve,
Uh-huh.
is just gonna suffice for all our purposes.
Yes.
Yeah.
Of course, if you could do better, then people would be very happy. Okay, so other questions? So far, so good? We have a chat. Maybe a nice exercise is instead of this bound for logarithm of zeta, suppose you had a zero-free strip. Yes, no zeros to the right of 1/delta for some fixed delta. Run this argument again to get the prime number theorem with the better error term. So that's exactly right. If we, instead of having, so let me just say what Lewis said again, all the way back here, and Riemann understood this and explained this. He said, if you knew that there were no zeros in an entire vertical strip, if this entire vertical strip had no zeros, then don't come to this line, come all the way to this line, and only do one estimate, and the one estimate is x to the 1 minus however far you could go, 1 minus delta.
And you get great savings.
Then you get a power savings. And he said, if the zeros really are on the 1/2 line, then pull the contour all the way to the 1/2 line and get x to the 1/2 plus epsilon.
Yeah, exactly. And then so even if it were to 0.99 or something, right, with enough digits, you'd be able to actually see the correct digits.
Exactly. You'd see some percentage of the digits being correct.
Yeah.
Right now, we don't even know that 1% of the digits are right. We know that 0% of the digits are right. You'll see in a second what error term we're getting out of this. And Lewis suggests another exercise is to prove such a zero-free region. Of course, that would be a great, exactly. Okay, so let's quickly, we're almost out of time. Let's put it all together. So on one side, we had a sum over Vomgold of n up to x, exactly what we wanted, with an error term that was like epsilon x log x. On the other side, we had a main term, which was x plus big O of epsilon x plus big O epsilon x, and some error terms. One error term is this x over epsilon t to the 1/2, just being very crude, x over epsilon t to the 1/2. And the other error term is, so this is large t savings, and this is small t, but going inside the zero-free region savings over epsilon. There's another comment. Thesis idea. Would be a great thesis. Okay, that's it. Now all we have to do is analysis. We're going to optimize the exponents. The first thing we can optimize is t. Let's first optimize t. So here, so we're just going to set these two terms equal to each other. The 1 over epsilon is they have in common. The x they have in common. The x to the 1 they have in common. So to optimize t, we need to set t to the 1/2 to be the same as x to the minus a constant over log t. Okay, let's invert both of these. So this is t to the 1/2 needs to be equal to x to a constant over log t. How do you solve an equation like this? You take logs of both sides. So 1/2 log of t is equal to constant over log of t log x. And here's why. It doesn't matter that I put a 1/2 here because it's just some constant. I don't care what it is. So I'll suck the 1/2 into the constant. Then I get a log t squared equals log x. So log t is equal to square root of log x with some constant. The constants are different on every line. And so t is e to the constant root log x. Now, just to compare that to any power of x, if you guys aren't used to these kinds of weird functions, if I take x to some power, x to some delta, that's e to the delta log x. So this is root log x, which is much, much slower growing than log x. And what do we save? We save x over t to the 1/2. T to the 1/2 is also e to some constant root log x. Okay, so when I put all of this together, so there's an x, there's a, let me put this bigger error term, although as you'll see in a second, we'll save arbitrary powers of log x so that can get sucked into what epsilon's about to be. Then there's a 1 over epsilon that needs to be balanced against x times t to the minus 1/2. X times t to the minus 1/2 is x to the 1 minus some other constant log root log x. Okay, so the t is gone. We've optimally chosen t, and now the epsilon is going to be gone. So we balance these terms by setting them equal to each other. So I have epsilon x log x is equal to 1 over epsilon x to the 1 minus a constant root log x. Oh, sorry, this is not x to the, that's something different. This is e to the minus, so this is x times e to the minus constant root log x. That's better. X times e to the minus constant root log x.
For the complex analysis, you did do the t part, right? The t and x part, but the epsilon.
But the epsilon,
there.
yep,
Yeah. Okay. So
I ran out of time.
what's new?
So there's x's on both sides. There's epsilons on both sides. Let me bring the epsilons here. I have epsilon squared is equal to e to the minus constant root log x with a factor of 1 over log x, which I can suck into the constant. I can take the square root and again change the constant. And so epsilon is the same, e to the minus some constant root log x. That's what I lose, but I can make it a smaller constant so that these things are still of the same order of magnitude. Okay, so playing with these constants, you get x plus big O, x e to the minus some other constant root log x in the end. So this epsilon changed the constant if you keep track of the constants, but it didn't ruin the flavor of the error term. So that's how you can do it in smooth form without computing anything difficult. Just following through Mellin convolution and inversion.
Wait,
This is it. That's it. So we smoothed by taking convolutions. We made a smooth function, not by choosing our favorite way of smoothing, but by saying any way of smoothing. Take any smooth function, turn it into a delta spike with an epsilon, factor. Convolve the function you want against it. Play with the Mellin transforms of the two. That turns into a product. There we can estimate things nicely, and then we optimize parameters at the end.
And the epsilons choose so that neither term becomes problematic to the other.
Exactly. Exactly. So you can already see it here. How should you balance this? Forget about this log x. How should you balance this? You should make epsilon be e to the minus c over 2 root log x. because that'll make this worse by replacing c by c over 2. It'll make this better by adding a factor of e to the minus c over 2 root log x, which beats this log x. So that's the prime number theorem. Of course, I didn't do the Hadamard factorization. I didn't do the I showed you the key ideas that go into this.
But the rest of it is well documented.
But everything else is there.
Like,
Yeah, exactly. And this is completely standard. You can find it anywhere.
Like I think in Apostle's undergrad number theory book, he does talk about all of this except this smoothing and optimization part you're talking about.
Well, that's what I mean. So this is exactly the thing that I have not seen elsewhere. Smoothing by Mellin convolutions. That's anyway.
Now this is not I mean, we're not getting every x over log beta, right?
This is better than any power of log, because look, if you have a power of log to the log x to the a, what is that? That's e to the a log x. How does that compare to what we saved, which is e to the root log x? Root log is still way faster than log.
So this is better than the Siegel-Wasfield formula.
This is way better than any x to log to any power. This error implies any power of log you want. Okay. What we have today, the best known results are an error term x times e to the minus, not log to some constant, not log to the 1/2, but log to the 3/5. So instead of log to the 1/2 being the amount that you save, it's log to the 3/5.
0.1. You say
Oh, yeah,
0.1 and
maybe
it's
so.
on
I was gonna say that.
Okay, so let me give you an exercise in the spirit of Lewis. Make that 3/5 1. If you can save minus some tiny constant log x to the power 1, that's x to the minus a constant. That's a zero-free region. That's a quasi-Riemann hypothesis.
And this implies the zero-free region.
Yes.
The other way around also.
Yes.
Okay, is it easy to see why the other way around also?
Yes, from the explicit formula.
What? I mean, if you have a zero-free, you can run this argument again, maybe, that's according to the suggestion, and you will see that you will get a power save.
Yeah,
Maybe.
if there is a term here, then it will fluctuate by that real part. In the same way that the prime number theorem will be off. So the fluctuation you can just read off right from this term. You have to do something to make it rigorous, but this was already understood. All right, any other questions or comments?
Yeah, I have a question.
Please.
So I'm realizing now that sort of the way that I originally learned how to do this back in like the second year or first year or whatever it was,
Yep.
it was slightly different because I used what you did is you took the actual like cutoff, the sharp cut, and then you convolved it with this thing that has very narrow support.
Yes.
And then what I did is I took the cutoff and then I just like said, okay, from x to x plus y, I'm going to just go down.
That's how it is in every textbook that I know of. Yes.
And then but it turns out that it's kind of the same thing in a way.
Yes.
Just a cosmetic difference, because ultimately you do have to choose epsilon in terms of x.
I agree completely. It's a cosmetic difference. The reason I prefer this way of doing it is that you don't have to think about how, if I want to take it like a straight line, and then how do I estimate the Mellin transform of this? It's going to be something weird.
Yeah, all the estimates are a lot easier if you're using convolutions. That's the
yoga.
Okay, and then there's one other thing that I wanted to ask about, which is, since you have positivity, like would it help you at all to just do upper and lower bounds?
Yeah, you can do that in this part of the argument. Where is it? Here. Here we have we have, if you replace x by x times 2 to the minus epsilon, and then x by x times 2 to the plus epsilon, you get lower bounds and upper bounds for the thing that you actually want. And we did it just by saying, okay, well, there's a region where we'll go between 0 and 1, and that region has length epsilon x times the value of Vomgold. So you can do it by positivity as well. You can argue by positivity, or you can argue by just what I said.
Because that would eliminate that whole, like that big O term that's there in like the second line from the bottom, like up from the bottom of that page.
Of this page,
Yeah, like that one you're right, your cursor is near.
it would
Like
eliminate
using
what?
positivity would eliminate that term, right?
Well, you would get
But that
upper
term will
bound.
come up again in another place anyway.
Yeah, first of all, the term will come up again. Second of all,
Yeah.
if you replace x by x times 2 to the epsilon, then you're guaranteed for this to be an upper bound for what you want. And you replace x by x times 2 to the minus epsilon, this is guaranteed to be a lower bound. So you can do that upper and lower bound if you want to. Yes, by positivity. But in this case, it's actually the same to just say, here's the region that's where we don't know that we're getting exactly a cutoff function. And it's a short region. It's a region of length epsilon x.
Mm-hmm. Yeah. All right, thank you.
All right. Any other questions?